Now, in order to understand what to do with this guy, I'm going to just describe very, very abstractly what we do and then carry out one example in detail. So to compute this area, we're going to follow initially 3 steps. First of all, we're going to divide into rectangles. And unfortunately, because it's impossible to divide a curvy region into rectangles, we're going to cheat. So they're only quote-unquote rectangles. They're almost rectangles. And the second thing we're going to do is to add up the areas. And the third thing we're going to do is to rectify this problem that we didn't actually hit the answer on the nose, that we were missing some pieces or choosing some extra bits. And the way we'll rectify that is by taking the limit as the rectangles get thin. Infinitesimally thin, very thin. Pictorially, again, that looks like this. We have A and our B, and we have our guy here, which is our curve. And I'm going to chop it up. First, I'm going to chop up the x-axis into little increments, and then I'm going to chop things up here, and I'll decide on some rectangle, maybe some staircase pattern here, like this. Now, I don't care so much. In some cases, the rectangles overshoot. In some cases, they're underneath. So the new area that I'm adding up is off. It's not quite the same as the area under the curve. It's this region here, but it includes these extra bits here. And then it's missing this little guy here. This little bit there is missing. And as I say, these little pieces up here, this little bit up here is extra. All right, so that's why we're not really dividing up the region into rectangles. We're just taking rectangles. And then the idea is that as these get thinner and thinner, the little itty-bitty amounts that we missed by are going to zero, and they're going to be negligible. Already you can see it's kind of a thin piece of area, so we're not missing by much. And as these get thinner and thinner, the problem goes away, and we get the answer on the nose in the limit.